Hello everyone. This video, I'm also want to show you some terminology in mechanics of material. Okay, and why I use this video format because I want to do some real stuff demonstration. Okay. And so first of all, let's first explain what's called elasticity. Okay, elasticity in 中文 means 弹性. Okay, but 中文弹性 sometimes will let you to misunderstood that it's elasticity. Okay, so let me demonstrate what's called elasticity. Okay, suppose I also have this rubber band. Okay, as a rubber band. Okay. If I apply a stress, okay, normal stress on this rubber band, okay, initially it's here, okay, I apply a stress, and then when I release the force, it can bounce back, it can restore, not bounce back, it can restore to its original state. Okay, the original state is here, and apply a normal stress or normal force, and after I release the force, it will come back to its original situation. Okay, that's called elasticity. That's called elasticity. Okay, that means it can restore, the material can restore back to its original state. Okay, that's called elasticity. For example, so actually, if you apply a stress, actually I can apply the stress on this glass. Okay, and I think when I apply the stress on this glass, it's very different. I apply stress, or I compress here. I make a large compress, but and when I apply this large compress, it will have very slight deformation. But maybe you cannot see it. It's difficult to see it. But after I apply this compress this glass, and I release my compression force, this glass will restore back to its original state. Yeah, but that's just what, like I said, the deformation is very small, so it's very difficult to see it. But after you release the force, it will back to its original state. Okay, that's called elasticity. Or we can say the material is in an elastic region. Okay, elastic region. So when it comes to the stress strain curve, it will look like this. Okay, when you do the tensile test, okay, this is the first part of your, and then here. Okay, so here we call this is called elastic region. Elastic. Okay, and in the elastic region, the stress and strain has a linear relationship. Okay, and the slope we call modulus. So it's a very important relation. The stress equal to the modulus times the normal strain. Okay, that's very important. Also, okay, and this is elastic region. Okay, elastic region. If the material in an elastic region, this situation hold. Okay, but once the material pass through the so-called yield stress. Okay, yield stress. Okay, once the material pass over the yield stress, okay, it's no longer elastic region, and sometimes we call it, okay, maybe after here we call it the plastic region. Okay, in plastic region, and in the plastic region, the material will have the permanent deformation. Okay, because we just say when the material in an elastic region, that means when in elastic region I make a deformation, I make a strain on the material, and after I release the force, the material back to its original situation. That's called elasticity and elastic region. Okay, so what is the permanent situation and the yield stress? Okay, so I have to sacrifice one rubber band. If I apply a very large stress on this rubber band and pass through its yield stress, and it never bounce back again. Okay, I watch that. Okay, if I apply lots of stress, very large, it's very difficult. Maybe I should. I think this is very This is a very bad example. I should choose the maybe much easier rubber band. Let me see. Okay, let's try this. I really want to pass its yield stress. Yield stress. Yield stress. Pass to its yield stress. Yield stress. Yield stress. That's not. Maybe I need more shape. Okay, maybe I need to cut this. Okay, maybe that's better. Okay, stress, strain. Okay, it still can bounce back right now. It still can bounce back right now. Okay, I make a lot of stress on this material. Permanent deformation. Yeah. Oh, still can restore. Okay, that's very. Okay. Oh yeah, that's very bad experiment. So I cannot really create a used because I want to show the permanent deformation of the rubber band, but looks like I cannot do it. Okay, maybe this. Yeah, because the video has time limit. Okay, so maybe I cannot show you the yield stress on time limit. Because yield stress, because it's just a break. It's just a break. It's not yield stress. Okay. So let's use the aluminum. So yield stress. So when I apply, if I compress this aluminum material, my compressed stress is over the yield stress, and it will have the permanent deformation like this. This is called permanent deformation. Okay, permanent deformation means the material cannot restore its to original state. Okay, so aluminum, when you compress, if you compress the aluminum over yield stress, you have permanent deformation like this, and it never restore back to its original state. Okay, and I just want to show you it's also happen on rubber band, but looks like the rubber band is very difficult to do such experiment. Okay, so the yield stress. Okay, so and the yield stress. One thing I want to mention is for the yield stress, after the yield stress, we can consider after the material has a permanent deformation, we can say the material is failed. Okay, so in the previous section we have a terminology called safety factor, and safety factor is the yield stress, so the fail stress divided by allowable stress. Okay, so the fail stress, and at that time I said the fail stress, yeah, sometimes you can treat the fail stress, it's just equal to the yield stress. Okay, after passing the yield stress, the material has permanent deformation or say plastic deformation, and we could say the material is failed. Okay, so that's the yield stress, the terminology for the yield stress, and then the next terminology is called brittle and ductile. Brittle material, ductile material. Brittle material means that your material has no yield stress, okay, but very hard, or very stiff. I would say very stiff, and no yield stress. Doesn't show any yield stress. And what is a brittle? But it's very brittle. Okay, it depends on the situation. It's not very good. Sometimes it's not very good. Okay, the glass is a very typical brittle material. Okay, glass is a very good example for brittle material. Or ceramic is also one, and concrete is also a brittle material. And in the class, I show that the video for you. When you compress a concrete, it doesn't yield, it doesn't deformation, it doesn't have any deformation like this. Okay, it doesn't have any deformation like the aluminum or like metal. It just break apart. Okay, same thing happens on the glass. The glass is also a brittle material. So when you compress or make a tensile on the glass, Yeah, it doesn't have the yield stress. It doesn't have any deformation. No deformation like this. It's just the break. If you apply the loading over a certain limit, it just the whole material just shatter around, just becomes shatter and becomes piece. Okay, it's no yield, no deformation. Okay. Okay, so and the other opposite situation is called ductile. Ductile, okay. Ductile means your material has yield stress. It can deform. Okay, it can deform. Well, that means it can deform. Okay, it can deform. Okay, and a brittle material, nothing, you cannot deform. Okay, it just break. It just breaks, shatter. If when you apply stress, extend over a certain point. So what's a ductile? Okay, metal often is ductile. Okay, metal is often ductile. Like this, the metal wire. Metal is ductile. You see, it's ductile. So that's why you can bend it. You can bend it. Okay, you can bend it. You can bend it, and it has a permanent deformation, right? Okay, you can bend it. Okay, you can bend it. Okay, you can bend it on this metal wire. Okay, that's called ductile. Okay, metal often show the ductile, and because metal is ductile, that's why you can compress the arm limit. Okay, because metal is ductile. Okay, you can deform. Okay, you can deform. You can deform. Okay, you can deform. Okay, you can deform. Make a deformation. And on the contrary, for the brittle materials like ceramic, okay, ceramic or glass, you apply a force, yes, keep pushing it, yeah, there is no deformation on glass. You cannot observe any deformation. Okay, so this is not ductile material. Okay, ductile material is the metal and this wire. Okay, it's called deformation because it can bend and deform. Okay, so that's the terminology for the brittle and ductile. Okay, and the final one we want to say, the final terminology is called Poisson's ratio. Poisson's ratio. Okay, Poisson's ratio is actually the deformation between the lateral. Okay, it's deformation. Deformation is like this. It's deformation of the. Let's see. It's a longitudinal. Okay, lateral divided by longitudinal. Let me check. Okay, longitudinal, lateral. Okay, lateral divided by longitudinal. Okay, yeah, it's sometimes very hard to understand these two words. Okay, so if you apply the material, okay, I draw a material here. Okay, it's apply the tensile loading. Okay, this is called longitudinal. Okay, and this is called lateral. Okay, so Poisson ratio actually is just the ratio between the strain, the lateral strain divided by longitudinal strain, and it's negative. There is a negative sign before it, because after you make an extension on the material, you have the longitudinal extension will make the lateral compression. Okay, so here I use this as an example. Okay, it's okay bone. Okay, I'm not sure how to say okay bone in English. Okay, so yeah, you say here the Poisson ratio. Yeah, if you apply the axial loading here, then apply the loading on longitudinal direction, you will see the contraction in the lateral direction. You see that? You see that? Yeah, you see that. If you keep you set as a shrink on the lateral direction, and I don't have enough force. Yeah, if you keep make an extension longitudinal direction, you have contraction. See the contraction? Okay, let me do it again. You see the contraction in lateral direction? It's not obvious, right? Okay, let's try it again. Here is a deformation here. Okay, let's see. Maybe here is easy to see. if you make a longitudinal extension, there's a contraction. Yeah, that's right, it's contraction. I hope you can see some contraction in the material. Okay, you see that? Okay. Okay, so maybe a little, okay, but not really obvious. Okay, so I final one, I make a demonstration on compression. Okay, compression much easier to see. Okay, so it's a material like this. Okay, yeah, if you compress your material, you will make an extension on the right. Make a compression on longitudinal direction. There's a expansion on the lateral direction. Okay, you see that? Okay, this is the material, and you compress it. Yeah, you see. Okay, before. Okay. See here, okay, if you compress the material, okay, here you compress material here. If you compress the longitudinal direction, there is expansion on the lateral direction. Okay, here, okay, or here, okay. You compress this direction, and there's an expansion on this direction. Compress, see it, compress, see it, compress, see it. Okay, compress, expansion on this direction, compression. Okay, and then if you make an extension, it makes the extension. It's a bit difficult to see the contraction. Okay, difficult to see the contraction. Okay, but you still can feel it. You still have some contraction because it's make a some contraction happens in the middle part. Okay, and then so this is so-called Poisson ratio. Okay, this is so-called Poisson's ratio. Okay, you apply a loading on the longitudinal direction, you will have a contraction or expansion on the lateral direction. So okay, so it's a negative. Extension, this here is a contraction. Make a compression here is make an extension on this lateral direction. So that's why it's negative. Okay, so here is some terminology for the mechanism material. Yeah, I make some different demonstration, but some of them are not very successful. But that's all I can do right now. Okay, so I just stop the video here and see you in the next video. Okay, bye bye.